evening, everyone. We are in the week 12 problem solving session of the NPTEL course Network Analysis, and week 12 is about ideal op-amp circuits. Let me share my screen. So, last week we have discussed about two-port networks as well as gyrator circuit, and this week, being final week, we'll discuss about op-amps and circuits that can be made using op-amps, basically ideal op-amps, and we'll also discuss few aspects about non-ideal op-amps also. So yeah, today's point of discussion is ideal op-amp. Op-amp full form is operational amplifier. So let us start. Uh, Ideal operational amplifier. Okay, so this is op-amp, simply called as op-amp. We can also call it as a differential amplifier. Basically, it will amplify the difference in the input signal. So that's why we can call it also as a differential amplifier. So basically, op-amp is an IC, so an integrated circuit, and you might have already used it in your UG. You might have used in your UG some of the laboratory courses where they might have given you some IC, 8-terminal IC, and you might have used it in making some connections, say filters or amplifiers or some are integrator, differentiator, some of the circuits. And op-amp is widely used in many applications. So it has like very big application network, so it can be used in any of the signal conditioning circuits. So wherever we will be using any amplifier, you can use op-amp, or if you want to subtract any two signals there, you might be using op-amp. Hello, Neetu Srivastava, am I audible? Hello, am I audible? Can you please confirm?
Yes, sir.
Okay, okay. Okay, so today we'll be discussing about op-amp. What I was just trying to say is, like op-amp is an IC, an integrated circuit. You might have already used in your one of the UG laboratory courses, and for amplifier or for filters. So it has wide range of application in many domains, and even in my research work, I'll be using op-amps. One big application, like one application where we use op-amps is to amplify signals. So in the circuits that we work on, it has currents, mainly inductor current, and voltages, capacitor voltage, something. So the sensed voltage or sensed current may be very small or large. So, but we want to be in certain range. So either we have to amplify it or we have to scale it down. So for that application, we use op-amps. And in my application, the topic that I work on, I use op-amp for amplification of inductor current, sensed inductor current, and it has wide range of applications. So it can be used to add two signals, or it can be used to subtract two signals. Also, we use comparators. So op-amp will also work as a comparator. So in the comparator, basically what happens is it will say which signal is higher than the other signal. So if one signal is more than the other signal, output will be high, otherwise it will be low. So this is just basic introduction, but we'll go into the details. But yeah, one question. Last week, no one has joined. Were you busy last week, or you forgot, or any reason? So one famous IC is the IC741, which is made by Texas Instruments. So it is uh, quite famous, and if you remember, it has 8 terminals. And if you want to see the structure of op-amp, it is something, it will look something like this. So it has a minus terminal, it has a plus terminal, and here This is the negative inverting input. So negative is called inverting input, and positive is called non-inverting input, and it needs a power supply. So it's an active. So it's a active component, which means in order for it to work, it needs some additional supply, resistor, capacitor, inductor, or passive. You just have to connect a source and it will work. But here the input is different and this supply is different. So this is say VCC, and this is our V naught output. So this I'll call say V1, and this I'll call V2. So the like the normal representation that we use in our day-to-day life is this side, like this one. But the actual IC will have 8 terminals or maybe more than 8 terminals, depending upon different IC structures. But this is quite famous IC, and so the if you see any IC, it has one dot, or there could be instead of dot, there could be some notch as well. So some ICs have this notch, which means that is the top side of the IC. But majority of the ICs has this. Sorry, majority of the ICs has this dot, which means that is pin one. So this is one, two, three, four, and then from four we'll have five, six, seven, eight. So this is the configuration of like pins. So the dot is one, and from there you go down, and then again from bottom you go to top. So the terminals are like this. So this is the negative terminal. So this is the inverting terminal. Two is the inverting terminal, and this is the non-inverting terminal. And this is the like either you can again there might be different op amps. One few of the op amps might be needing plus VCC, minus VCC, and few might be needing only plus VCC and ground. But plus VCC, minus VCC is most widely used. So it depends upon the op amp. So you have to check their data sheet and see what type of supply it needs. So widely used op amp, the IC741, it needs plus 12, minus 12, or plus 15, minus 15. So the voltage should be can vary from 12 to 15. So it can be plus 12, minus 12, or plus 15, minus 15. So this is the plus VCC, and this is this minus VCC, and terminal 6 is the output. So this is the output. So if I write the terminals here, this is terminal 2, this is terminal 3, this is pin 6, and this is pin 8, and this is pin 4. Okay, so this is just the representation of the op amp. But how does this op amp work? So let me just copy this. Basically, it works like a differential amplifier. So depending upon the input, the output will vary. So if we draw the graph, so it basically looks something like this. And if I draw vertical line, so this first region is called linear region, and this is the output. Sorry, this is the output V naught, and this is V2 minus V1, positive minus the negative. So non-inverting terminal minus the inverting terminal. And this region, if you see this region, this is called linear region, because if you see it is linear, and this top region is called saturation region. Okay. Now, what is this maximum voltage value? This is plus VCC. So the positive side of the power supply that we are giving to the op amp, and this is minus VCC. So who decides this linear region? Okay, we'll come back to that point. So if I consider the slope of this line will give me the gain of the op amp. Gain of op amp. Okay. So this is the gain of op amp, and usually it is represented by this symbol A. So what happens if the gain is high? If the gain is high, then the linear region will be small. And if the gain is small, then the linear region will be high. So I can say, like, if the op amp is operating as an amplifier, it operates in the linear region. If the op amp is operating like a comparator, then it operates in the saturation region. So for comparator, linear region should be small. For amplifier, linear region should be more. Okay. So now what happens is, say, if we consider when ideal op amp. So this is for non-ideal op amp. So ideal op amp will not have any linear region. So we'll get back to it. You are following, right? Hello. Are you able to follow? Okay. If you have any doubts, you can ask me. Don't wait till I stop. Okay. Someone mentioned in the chat. Yes, sir. Okay. So this is that gain. And if I want to see the circuital representation of this op amp, how I'll be looking. So I'll just write. So this is, so the op amp has input resistance, output resistance, and gain A. So how I'll be representing it? So this is our V1, and this is our V2. This is our R in, and this is A into V2 minus V1, and this is our R naught, and this is our V naught. So this is our inverting terminal, and this is our non-inverting terminal. So we are giving this V1, V2. So if I draw a box, so this box is the op amp, and all the values are with respect to some common ground. So V1 is with respect to this ground, V2 is with respect to this ground, and similarly V0 is with respect to this ground. So if there is a non-ideal op amp, then it has some finite Rin, gain, R naught. What if I consider non-ideal op amp? Sorry, ideal op amp. So what is the condition that needs to be met so that we can say it's an ideal op amp? First of all, for the ideal op amp, if we consider R in, if we consider gain, and if we consider R naught, Rin should be infinite, as if it has very high input impedance, and gain should also be infinite, and R naught should be 0. So now if I ask you, what happens if the gain is infinite? So if you consider this one, this is for some non ideal op amp. Here it has a finite gain A, right? Now if I make this A infinite, it becomes vertical, isn't it? So if I consider one ideal op amp, say, now I am considering ideal op amp. So here basically say R naught is 0. In this case, say R naught is 0. Then what is my V naught? V naught is A into V2 minus V1, right? So that also, let me write, it's also a key result. So if R naught is equals to 0, then we have V naught is equals to A into V2 minus V1. Okay, so this is one key result that you need to keep in mind. Okay, so now let us consider one ideal op amp minus plus. This is V1 and this is V2. And power supply, I'm not writing, but it is assumed that it has power supply. So plus VCC minus VCC, I'm not writing, but it's a good idea if you write. But even if you do not write, it is assumed that it has power supply and it is working like an op amp. So if I consider ideal op amp, then the circuit will be something like this. Got it? So this is our plus VCC and this is our minus VCC and this is our V naught and this is our V2 minus V1. So there is no linear region as if it is working like a comparator. So it is working like a comparator, right? What happens if I write V naught? V naught is equals to plus VCC or minus VCC, and plus VCC is if V2 is greater than V1 or V2 minus V1 is greater than 0, and this is V2 is less than V1 or V2 minus V1 is less than 0. So it is working like a comparator and it is having that straight line and no linear region. So for this ideal op amp, these conditions are like met. Rin is infinite, A is infinite, and R naught is also 0. So now if you consider one quick example, let me consider this ideal op amp only. So let me consider this. Let me just copy paste it here. Okay. So in the case of V1, so let us consider ground. So say V1 is grounded. V1 is grounded. And this is assumed to be ideal op amp. Okay. Now say I have considered one, sorry. I will be considering one input and I will draw the corresponding output. Okay. So this is my V2 because V1 is 0. Now V2 minus V1 is nothing but V2. And this is my V0 and this is my time T. So now I'll consider like this is my say time period. So this is my time period. Say I have considered, okay. This is the half time period. This is also half time period. Say I have considered one sine wave like this. So now what is my V0? Say I'm considering this ideal op amp. So this is my V0, either plus VCC or minus VCC. So how it will be? Can you tell how my V0 will look like? Anyone? Neetu Srivastava, can you tell me how this V0 will look like? Okay, so if we go back to this waveform, we can see that here V1 is 0. So if V2 is greater than 0, it will be plus VCC. If V2 is less than 0, then it will be minus VCC. So it is basically working like a comparator. So I can say that for this cycle, it will be plus, this cycle, it will be minus. And the same thing, for this cycle, it will be plus, and this cycle, it will be minus. And it will continue. Okay. So this is my, so here there is plus VCC and here there is minus VCC. So this is our plus VCC, this is our minus VCC, this is our plus VCC, this is our minus VCC, and this is our plus VCC. So this is for ideal op amp. So what happens for non-ideal op amp? V2 minus V1, this value and this value. So what I'm trying to say is this value and this value will be very small because the gain is very high. So the V2 minus V1 should be very, very small for it to work like an amplifier because the gain is very high. And if you see, if the gain is infinite, there is no linear region and it is almost at zero. But if the gain is very, very high, but not infinite, then it will be very, like the slope will be very high. So the V2 minus V1 that needs to be present over here for which this op amp will work like an amplifier will be very, very small so that we can get it from here. So if my op amp is working like an amplifier, then V2 minus V1 will be V naught by A. So as A increases, V2 minus V1 will decrease. So for very high value of A, V2 minus V1 will be very close to zero because A is very high. And if A is infinite, then V2 minus V1 is close to zero. Okay, so this is some basic introduction about op-amp. Now we'll go to something called inverting amplifier. So we'll discuss now how op-amp will work like a inverting amplifier. I hope you are following. Are you following, or if you have any queries, you can ask. Do you have any doubts? Okay. If you have any doubts, you please ask because this is the last week and op-amps are very, very important. If you understand the concept, they are very easy to solve. But if you do not understand, then it will be difficult. So inverting amplifier, the structure is something like this. Minus plus and plus is grounded and minus we have one resistance and plus we have another resistance. And this is my V1 cell and V2 is 0. This is my R1. This is my R2 and this is my V0. And here we have that R in, right? Okay. So now what will happen? If the op amp is ideal, then we know that first of all, Rin will be tending to infinite and gain will also be tending to infinite. Okay. And R naught is 0. This we know. Now, if you see, say this is my VA and this is my VB. Also, VB can be V2. So this basically, these are my V1, V2 terminals inputs and VA, VB are the voltages at this minus and plus because there is a resistance here. VA and V1 are not same. So here I mean to say is VB is equal to V2. Or for confusion, if you are getting confused, you just remove. So these are my V and VB terminals. So if you get back here, if it is working like an amplifier, I know that V not equal to A into V2 minus V1, or here it is VB minus VA. So I will get my VB minus VA is nothing but V naught by A. And if A is tending to infinite, then if A is tending to infinite, then I'll get VB minus VA is equals to 0 and VB equal to VA as if they're shorted. And this is one very important aspect. So this is called negative feedback because a resistor is connected in between output and the negative terminal. So when any op amp is converted in this negative feedback fashion, then this minus and plus, so the inverting and non-inverting terminal are virtually shorted. So we can say that inverting and non-inverting terminals are virtually shorted because the gain is very high. So if it is virtually shorted, now let me draw this circuit again and we'll get back into the discussion. Okay, so this is our circuit. So now if I erase this, V and VB are 0. Okay. Now if Rin is infinite, if the resistor is infinite, the current drawn by it will be 0. So the current that is entering the op amp will be 0. So whatever current that is coming over here will pass in this way. Say this is my terminal A, and if I apply KCL at A, then current entering should be equal to current leaving. Current entering is V1 minus 0. Why 0? Because these are virtually shorted. So V1 minus 0 by R1 is equals to 0 minus V naught by R2. So if you solve this, you will get V naught is equal to minus R2 by R1 into V1. So the output is scaled version, but inversion of the input. So if V1 is positive, V naught will be negative and a scaled version. If I consider R1 equal to R2, then V1 will be minus V naught. So if I send a sine wave, then output will be 180 degrees phase shifted of the sine wave with a scaling factor of R2 by R1. If I make R1 and R2 same, then it is just inversion of the input voltage. So this is called inverting amplifier, and the key aspect that you need to remember is in the negative feedback fashion of any op amp, the inverting and non-inverting terminal are virtually shorted. Here, because this is connected to ground, this is connected to ground because these are two shorted. But if this is connected to some voltage V1, then this VA will also have the same potential V1. So the idea is these are virtually shorted. So these two are as if they are shorted internally. Why this is happening? Because we have considered the op amp to be ideal. So is this clear until this point? Hello, hello. Is this clear until this point? Okay, someone has mentioned in the chat. Yes, sir. Okay. If you have any doubts, you can ask until this point. And now we'll go more into different circuits that can be made using op amp. So, but before we go into further discussion for this, uh, whatever amplifier that we have discussed, let us solve few problems. So, problem one. So these are the problem that Sir has considered or taken or explained in his session, the online video. So I am considering the same example. So let me consider one op amp minus plus, and kindly note that the non-inverting terminal is grounded and not the other way around. This is V naught and this is V1, and this is 2K, and this is 4K. Now if say this is ideal op amp, which means the gain is infinite and these two are virtually shorted, and whatever current that is coming in this direction will flow like this, and we got V naught equal to minus R2 by R1 into V1. So we can apply the same thing. V naught is equals to minus R2 by R1 into V1 because this is my R2 and this is my R1. So from here we will get V naught equal to minus 2Vn. So it is inverting, but a scaling factor of 2 is there. Okay. So this is when we consider ideal op amp. Now, what if we consider a similar inverting amplifier and we consider non-ideal op amp, which means there is finite gain and the input impedance is also not infinite. Then how to solve? Let us solve. Problem 2. So this same problem we'll consider. So let me just copy paste. Okay. And here instead of, sir, why always non-inverting grounded? What happens if inverting is grounded? So you can also short this inverting terminal to be grounded, but our point of discussion here is inverting amplifier. So that's why we consider this input at the inverting terminal and out this non-inverting terminal is connected to ground. So what happens if this is not connected to ground? That is a good question. So let me first answer that. So what happens if this is not connected to ground? Okay. So if this is not connected to ground, say I have connected it to some voltage V1. So I have connected to one voltage source, say V V naught. No, then it will be output. So I'll say V dash. So now what happens? This terminal are virtually shorted. So this also will become V dash, right? So now if I apply KCL, then we'll get V1 minus V dash by R1 plus V dash minus V naught by R2 is equals to 0. So now in this case, V naught is equals to what will be the value? Mhm. So if I can take V naught on the other side and multiply R2, then we'll get R2 by R1 into V1 plus V dash minus R2 by R1 into V dash. Is this okay or are we making any mistake? Just okay, sorry, this is not plus, this is equal to. So because current here and current there are same, this is equal to, so there is a mistake over here. Let me draw it again. So we have V naught is equal to minus R2 by R1 into V1, then plus R2 by R1 into V dash minus V dash. So we'll get something like this. So in this case, we notice some other value, but it is connected to some other voltage source. But if V dash is 0, then it will be minus R2 by R1. So we needed to work like an amplifier. So there will be just a direct relation between input and output. So output is some gain A into V1. A can be positive or negative, but in this case it is negative. But if you can connect it to some other voltage source, then it will be like a different value. Amplifier plus some offset voltage is also coming. So I hope, okay. So you have also asked what happens if inverting terminal is grounded. So if inverting terminal is grounded, then basically we are considering this virtual shorted when there is a negative feedback, which means there is a resistor connected in between R2 as well as this minus. So that's why we connect a resistor here and another resistor here. So the structure itself is for this inverting amplifier. We cannot directly connect this minus to be 0 for any amplifier because we want this negative feedback. For that purpose, you cannot directly connect this to ground. Whereas there is another amplifier which is called non-inverting amplifier. So the structure of the non-inverting amplifier is, instead of directly converting the inverting terminal to zero, we'll connect in this way. Minus plus. So we want that negative feedback. Okay. Now this is our V1 input or V in, say. This is R1, this is R2, and this is grounded. And now this is my V0. So by means of virtual short, this is my V in, because this is the same, and current entering equal to current leaving. So I'll have 0 minus V in by R1 is equal to V in minus V0 by R2. So if I bring everything on the LHS side, V0 by R2 is equal to V in into 1 by R1 plus 1 by R2. Okay, now if I multiply by R2 on both sides, I will get V0 is equal to 1 plus R2 by R1 into V in. So this is what we got. So if you see, there is no negative sign and the gain is always greater than 1, because 1 plus R2 by R1. The minimum value is R2 equals to 0. So then in that case, V0 equal to V in. But if R2 is some positive finite value, then V0 is always greater than V in, but the gain is positive. So this is called non-inverting amplifier, and this is how it needs to be connected. Yeah. So if you directly connect inverting terminal to 0, there is no benefit as such that we'll be getting, because we always want that negative feedback. So that's why, like, no circuit, no amplifier circuit will have that directly connected to ground. There will be always this resistor. Positive feedback can we connect? Yes, there are certain circuits where positive feedback is there. One such circuit is Schmidt trigger, even though it is out of the syllabus of this course. I'm telling it is like a Schmidt trigger. So with the positive feedback, what happens is like the output will keep on increasing and it will get saturated. So in the application of Schmidt trigger, it is used, and in that case, it works more like comparator, because it has that positive feedback and output will keep on growing and it will get saturated, because the maximum we know that the op-amp can give is plus VCC and the minimum value it can give is minus VCC. So majority of the applications, except that particular application, Schmidt trigger, op-amp is always used in the negative feedback, because we want the op-amp to be operating like an amplifier. So for that reason, only negative feedback is used, and in majority of the cases, negative feedback is only used. So yeah, the negative feedback has wide application, and positive feedback also has few applications, but very like focused on to particular application only. Any amplifier, differential, non-inverting, inverting, or integrator or differentiator, all are having the negative feedback. Okay, so yeah, that is the whole discussion about why we use negative feedback. Now, previously we were discussing this problem. Here we have considered ideal op-amp. Now, instead of ideal op-amp, we will be considering non-ideal op-amp. So in the case of non-ideal op-amp, the input impedance is not infinite, gain is also not infinite. So I'll consider whatever sir has given in his lecture. So Aryan sir has considered 100 kilo ohm, very high but not infinite, and gain also very high but not infinite, and say R naught is equals to 0. Then how do we solve? So we can say that there is this input resistance, very high input resistance R in. And now say this is my voltage VA. Now VA and ground are not shorted because it is not ideal. So VA has some very finite value, because if you go back again here, if it is working like an amplifier, then V1 minus V2 has some finite value. But if it is not, if it is ideal op amp, then in this case, both V2 minus V1 are zero. So that's why V1 is equal to coming V2. But in this case, in this linear region, if it is working like an amplifier, then V2 minus V1 is some finite value. So V2 is not equal to V1. So here my this terminal VA and this terminal whatever voltage, those two are not equal, but VA is very very small finite value. So now if you want to apply KCL here, so if you see now there will be current flowing in this direction also. So whatever this magenta we cannot equal now, but we can still apply KCL at the terminal. So apply KCL, then we'll be getting V1 minus VA by 2K is equal to VA by Rin is 100K plus, there is less than a minute. So if this meeting end, kindly join back so we can continue our session, plus VA minus V naught by 4K. So this is our equation 1. And we also know from this graph that where this equation V naught equal to A into V2 minus V1, right? So V naught is equals to, so V naught equal to A, which is 10,000 here, into this terminal minus that terminal. So 10,000 into 0 minus VA. So V2 minus V1, 0 minus VA. So this is second equation. So we have two equations, two unknowns. V input is given. So this is given. So this is given. So we have two unknowns, VA and V naught. So solve these two equations. So we have to solve. So we have to solve these two equations to get our V naught. But even if you solve and do, you will still get V naught very close to minus 2 into V1, because the gain is very high, but it will not be exactly 2. It will be minus 1.99 something, because our gain is very close to ideal, because this is high, this is high. So as if it is very close to ideal op amp, and for that reason it will be very close to 2 V. Whereas in the case of ideal, it will be exactly minus 2 V. So that is the difference. If the given op amp is not ideal, then you have to solve in this way. So is this clear until this problem? Now we'll move on to different circuits that can be made using op amp. Is it clear, or do you have any further queries until this point? We have discussed only the inverting amplifier and few aspects of the fundamentals. If you have any queries until this point, you can ask. Now we'll quickly go to differential amplifier and other circuits before we go for problem solving session. Now V naught is equals to minus 2A. So in this case, this is a non-ideal op amp. So these two are not shorted. So VA has some finite value. And I have assumed VA to be finite value. And there is one internal impedance over here, Rn. So this current, I know that it is not zero. So I have applied KCL over here. So this current equal to this plus this current. So this current is V1 minus VA by 2K is equal to this current is VA minus 0 by Rn. So VA by 100K. And this current is VA minus V naught by 4K. So this will give me one equation. And the other equation is this equation that we know. V naught equal to A into V2 minus V1, because R naught equals to 0. Then V naught is A into V2 minus V1, because R naught is 0. So here also our question has R naught 0. So V naught equal to 100 into V2 minus V1. So this is my non-inverting terminal, 0 minus inverting terminal V. So this V1 is given. First we need to substitute VA in this equation, and we have to get a relation between V naught and V1. If you calculate it, it will be very close to minus 2, not exactly. So that's why I have used this symbol. So uh, this is this symbol. So this is equal to, and this is nearly equal to. So this is nearly equal to. So it means that it is not 2, but it is approximated to it. because our gains are very high and it is close to ideal op-amp, you will still be getting the gain close to -2, but not exactly -2. But if you say instead of 100, if you consider this is 10 to the power 5, right? If you consider 10 to the power 9, here also instead of 10 to the power 4, you consider 10 to the power 6 or 7. Then it will be very close to -2 because it is very close to ideal op-amp because A is tending to infinite, which means very, very high, and Rn is also tending to be infinite. So that's why I'm saying it will be -2. If you calculate, you can calculate later because this is some very small calculation I'm not doing now. So that's why I have said it will be close to -2. And in the case of ideal op-amp, it will be exactly -2. But whatever op-amp that we'll be using are not ideal, but they are very close to ideal because their input impedance is very high and gain is also very high. Okay, so now we'll discuss another important topic, which is the differential amplifier. So differential amplifier means it will amplify the difference in between the input terminals. So the circuit is something like this, minus, plus. So this is ground. And say this is V1, this is V2, this is R1, this is R1, this is R2, this is also R2, and this is V0. So say this is ideal op-amp again. Then we know that this current is 0, this current is also 0. And say this is my VA and this is my VB. So I can write VB equal to R2 by R1 plus R2 into V2. Do you agree? Because the other current is 0 as if it is working like a potential divider, like using resistance. So resistor divider. So is it clear how I'm writing VB R2 by R1 plus R2? Because the current in this is 0 because it is ideal op-amp.
Yes, sir.
Also, I know that VA is equals to VB. So now if you apply KCL, the current entering here will go like this. So we will get V1 minus 0 by R1 is equals to 0. Sorry, not 0. It is VA. My mistake. VA. And this is also VA minus V0 by R2. Right. So if I substitute, if I multiply by R2 by R1, we'll get R2 by R1 into V1 minus R2 by R1 into VA is equal to VA minus V0. So if we bring V0 on the LHS side and keep everything on the RHS side, we'll get minus R2 by R1 into V1 plus VA into 1 plus R2 by R1. And this is our VA, right? Which is also equal to VB. So you substitute this here. Now I will get V0 equal to minus R2 by R1 into V1 plus VA is R2 by R1 plus R2 into V2. And this is R1 plus R2 by R. So what will get cancelled here? The numerator and denominator get cancelled and R2 by R1 into V2. So now this can be written as V0 is equals to R2 by R1 into V2 minus V1. So the difference between the input V2 is the voltage at the non-inverting terminal and V1 is the voltage at the inverting terminal is amplified by the factor of R2 by R1. If R2 is equals to R1, then the scaling is 1. But I can play with R2 and R1 and I can play with the gauge. So this is the circuit I also use in my research work. So I get a signal at these 2 points, V1 and V2. It may or may not be ground. V2 could or may or may not be ground, but in my case, it is a finite value. This is also a finite value. So V2 minus V1, I am trying to amplify with some other voltage. So I play with R2, R1. So I say R1 I consider 1K, R2 I consider 10K. Then my amplification is 10. Because say this, my input is 10 millivolt. I want output to be 100 millivolt or say 200 millivolt. Then I'll consider gain to be 10 or gain to be 20. Now, if you consider the practical implementation, the gain needs to be 10. So R2 by R1 is 10, but R2 can be 10, R1 can be 1, R2 can be 10K, R1 can be 1K. So it again could have infinite possibilities. So there are, if you consider practical implementation, there are multiple aspects that can come into picture. Like first of all, R1 and R2 should be little bit high. It cannot be very small. So it should be a few kilo to few tens of kilo or maybe. So say if I consider 1K, then R2 should be 10K. If I consider R1 to be 10K, R2 should be 100K. Now, how will I choose? There are again few aspects that come into picture like cost. If I can get the same gain using 1K, 10K, 10K, 100K, I'll choose the least cost because 10K and 100K may not be of the same cost. 100K might be costly, might be cheaper. So I'll check which is more cheaper for me, which will save me price and which will give me the same output, which is a gain of 10. So I consider the cost into picture and also the availability of the like register. Maybe 100K is not available at that time. Then I'll not choose 100K. If say 20K is and 2K is available, I'll consider 2K, 20K. So my main objective is to get the amplification. So I'll consider whichever is available in the market at lesser price. I'll consider that R1 and R2 and I'll select. So these are some practical challenges and issues that I have faced, and that's why I'm sharing this knowledge. So 101 ohm, yeah, that can also be considered, but usually this resistor should be little bit high, else there will be loading effect. So this resistor should be like in the data sheet they'll give. So it would be better if they're at least in kilo ohms. So at least 1K. Below that, it is not recommended to use. So it will be mentioned in the data sheet again. So they will say minimum you have to use around 1K. In some cases, it could be lesser also, but whatever I'm using, it is at least 1K. So R1, if you fix 1K and R2, you can put 10K. But if it is at least 1K, R1 can also be 10K. That's what I'm saying. So R2 should be 100K, but R2 might be costly and may not be available. So these are some practical issues that can come into picture. So this, so that you will keep in mind, like how to select R2 and R1. It can be any value. They have infinite possibilities of R2 and R1, but there are some practical constraints like availability, cost, all this coming. So this is differential amplifier. Now we'll talk about integrator and differentiator. Integrator circuit. So integrator is also like a inverting amplifier, but here we have a capacitor, and this is all grounded. Say this is my V naught, V in, this is R, and this is C. Okay. Again, say this is ideal. Then I know that this terminal is grounded and this current is zero. So whatever current that is flowing here will also flow here. So IC, IC current flowing through capacitor is C into dVc by dt, right? dVc by dt. And C into what is the voltage across capacitor? 0 minus V naught. So dV naught by dt with a minus sign. And what is IC? V in minus 0 by R, right? So this is equals to V in minus 0 by R. So if I write V naught, then V naught is equals to minus 1 by RC integral V in dt. So the output is the integration of input. So that's why it is called integrator. Because it is minus 1 by RC into integral V in dt. But if you want positive, then you put another inverting amplifier of gain -1. So the overall it will be 1 by RC into integral V in dt. So similarly, like this integrator, we also have differentiator. Okay. So in this differentiator, R and C are interchanged. So we have minus plus, and here we have capacitor, and here we have resistor, and other things are the same. So this is my V in, this is my C, this is my R, this is my V naught. Again, this current is 0. So whatever current that is flowing here will flow here. So now IC is equals to C dVC by dt. Now it is d into Vc is V in, right? V in minus 0 by dt. Okay. And this is equals to 0 minus V naught by R. Now we'll get V naught is equals to minus RC into d V in by dt. So the output is like a derivative of input. So that's why it is called differentiator. So is this clear how we are getting integrator and differentiator? Yes. Okay. There is another general impedance transfer circuit that Sanjay has discussed, but I'll leave it up to you whether you want me to discuss that topic also or want to go to problem solving session because we have 1 hour left. So if you want me to solve problems, then entire 1 hour we can dedicate to problem solving, so we can solve more. I also feel that would be good. Or if you want me to also cover that concept, then it may take around 10-15 minutes. So then we'll get around 45 to 50 minutes problem solving. So I'm fine with anything. Just whether we should start problem solving session or we should also consider this circuit. What is that concept? So it is like general impedance transfer circuit similar to gyrator. So in the gyrator, if you see, we got this inverse relation of the impedance, right? So if I use capacitor, I will get inductor, emulated inductor. Without using inductor, the input impedance is seen like a inductor. Similar thing can be implemented using op-amp. So the input impedance is inversely proportional to one of the impedance. So if I use capacitor, then it will act like an inductor, which sir has covered in his lecture. And yeah, so like it is just another application of gyrator. It's not exactly gyrator circuit, but a different circuit where we get this inverse application. So yeah, like if you want me to cover, I'll cover, but there will be some time that needs to be taken from problem solving session. So that's why I'm asking. Whichever way you are comfortable with, we can go with that. If you're comfortable with problem solving, then you can just say that sir, please go ahead with problem solving, which is also fine. It is up to you because if you are want more problems, then we can solve more problems. So okay, some student is saying, sir, please explain this concept. So I'll just quickly explain this concept and then around 7:15 we'll go to problem solving session. So this is general impedance transfer circuit. So there are first of all 4 resistors. V naught, and then there is this load impedance. I'm representing it as a resistor, but it could be any impedance, capacitor or any other thing, but here I have represented as like this. So this is my V input and this is my V naught. Say this is Z1, Z2, Z3, Z4, and this is Z5 or say Z load, whatever, Z load. Now we have one op amp over here. So the circuit is something like this. Same thing we have over here. Plus over here, minus over here. So this terminal goes here and this terminal goes here. And this point is connected over here and this point is connected over here. Okay. The circuit will be a little bit complicated, but trust me, it is not at all complicated. So we'll solve. So all are ideal op amps. So assume ideal op amp. Then we know that virtual short. So if this is V in, this is V in, right? And if this is V in, then this is also V in, right? Because it is virtually shorted. Now Z1 and Z2 say current here is negligible, right? So current here is zero and current also here is zero. Current in this is also zero and current in this also is zero. But current here is non-zero. So we do not know the current. Okay. So now say current I1 is flowing. The input current is say I in. The same current will flow over here also I in. Is it? Do you agree?
Yes, sir.
So if this is IN and we do not know this current, say this one in this it is I2. Now can you realize Z1 and Z2 are parallel circuits because one of the terminal is connected over here and the other terminals are shorted. So Z1 and Z2 are parallel, right? So I can say Z1 and Z2 are parallel. Do you agree? So now, if they are parallel, the current into impedance should be equal to voltages, and voltage is same because they are parallel. But if you see the current direction is in the opposite, so I will get Z1 into I. So I'll get Z1 into I is equals to minus I2 into Z2. Because if you see, say this is my positive and the current is flowing here, and now this is my positive and the current is flowing here, but here the current direction is in the opposite way, which it should not be, so that's why that minus sign is coming. Got it? Or if you apply KVL here, then also it is fine. So it will be in into Z1 plus I2 into Z2 is equals to 0. So we'll get this minus. Got it? So now if this is I2, this will also be I2 because this current is 0 and this current is 0. Agree?
Yes.
Now, if this current is 0 and the load current is IL, then this current will be IL.
Right.
So now, also Z3 and Z4 are in parallel because the one terminal is virtually shorted and other terminal are connected. So Z3 and Z4 are parallel. So now I will be getting Z4 into IL is equals to minus Z3 into I2. Now, if you divide these two, we will get Z1 IL by Z4 IL is equals to Z2 upon Z3. Now, what is IL here? IL is nothing but V naught by ZL or V in by ZL, right? Because V naught equal to V. Agree.
Yes.
So now if we substitute that over here, we will get Z1, ZL, I in by Z4, V in is equal to Z2 upon Z3. Okay. Now if we multiply, so now basically what I want is the input impedance. Input impedance Zin is equals to V input by I input, and that will come to be V by N is Z1, Z3, ZL by Z2, Z4. Agree? Agree.
Yes.
So now Z1 equal to Z2 equal to Z3 equal to ZL equal to R and Z4 equal to 1 by SC, like capacitance. Now what will happen? If you calculate Zin, we'll get Zin equal to R cube by R. So it will be R square SC. So if I calculate write in a different way, it is S into R square C, as if S into L equivalent. True?
What is that L equivalent?
L equivalent is R square into C. I am writing L equivalent is R square into C because SL is for inductance, right? 1 by S is for capacitance, SL is for inductance, right?
Yes.
So if I get S into some constant, I can assume that it is acting like an inductor. So if I consider Z4 to be capacitor and all other to be resistor, then if I look at the input side, then my input impedance will look like as if there is a inductor connected over here, but we have not used any inductor. We have used only op-amp and we have used only resistor and capacitor. So we can emulate inductor using capacitor, similar to gyrator. Also, we can emulate capacitor using inductor. So this is one different application of op-amp. Like we can emulate inductor using capacitor.
I mean, what is the real application for this? Because we do have capacitors and inductors.
Yes, yes. So, yeah, that is a good question. Thanks for pointing out. So sometimes what happen is the inductor could be large and we don't want it to occupy space. So what we do is we emulate inductor using this, we emulate inductor using such circuits. So because capacitor value is very small, right? Uh, Also, if you say your inductor value is very, very large, and in order to get or buy that large inductor, say the cost is more, also it occupies very large space. So instead, I can connect R square into C. So I will choose R in such a way that R and C such that I will get this R equivalent. And resistors are very less cost, and capacitor is also very less cost. So I and two op amps. So I can get that inductor using this type of circuit so that I can emulate that inductor. So instead of connecting that inductor, I will use this circuit as if it will work like an inductor. But not, this is not used in many applications, but it can be. So the main objective is that we can use op amp for wide range of application. This is one application where you can get inductor characteristics using resistor and capacitor. So where you cannot get such big value of inductors at like lower pricing price, then you can use basic op-amp circuit and resistors and capacitors, and you can emulate it to work like an inductor. Keep in mind that these are very low power circuits. It cannot be used for very high power. In that case, you have to buy the inductor. So this is only for low power applications. Is that clear?
Yeah, I understand that very large inductor values might not be available, but space wise, two op amps, multiple resistors and capacitors are definitely going to occupy space.
No, no, like yeah, but that is a good thought from you. But resistors are very small. If you see any resistors that you have used on your breadboard, resistors are very small size, and capacitor is also very small size because these are low power. First of all, these are low power, so low power resistors are very small, and capacitors are also very small. And op amp, it is just four terminal device. So if you try to properly connect it in a way, then the space can be really small because it need not be connected on a breadboard. It can be made on a PCB, and if you place them very close to each other, and if you try to reduce the space, they can be made very small. Whereas inductors size is a constraint. If you see any inductors of very less current rating, also inductor size are very small. So even if you consider my application or in any application, inductor size is a constraint, not the capacitor size, because inductor size will drastically increase with the rating, power rating. Also,
Only thickness, right?
yes,
Thickness of the inductor.
as well as the area will increase. And in many applications, inductor will that constraint for space. So nowadays, people wants to try to reduce that space are trying to concentrate on how to reduce the size of the inductor, because inductor size, the height also is posed by the inductor. If you compare the height of inductor as well as height of capacitor, inductor will be putting that value. So inductor will be more tall than capacitor, so that can also pose that pressure. But these kind of circuits are not used directly in the application. These are very focused applications, but these are not directly used in many applications. Like in many applications where inductor is used, they do not use this type of circuit. We are just trying to show that it can be used and it will work because we also have this gyrator experiment in our second year UG lab, where we'll connect only resistor and capacitor and we'll show that it will work like an inductor. So we'll see the phase difference between input voltage and input current, that 90 degrees phase shift. So it is just an application, but
Sorry to interrupt you. Maybe when you are speaking close to the mic, right, then we are able to hear you.
okay, sorry.
Or
So
else,
now I think it should be fine.
y- yeah, now it is
Okay.
better. Yeah.
Actually, that this mic is far away from my mouth. Yeah, so these may not be directly used in many application, but it still can be used to emulate inductor. But it depends upon how good you want, because this also has many issues. It will not work like an inductor throughout the frequency range. So depending upon the frequency, it may or may not work like an inductor because it also has some different challenges. But the objective is it can be used to emulate an inductor without using actually an inductor. Yeah. So in your application, if this circuit can be used and if you want to test, then it will work and you will get benefited, but it may not be the solution for all inductor related application.
Just I'm thinking loud, right? So in order to emulate this inductor or capacitor, which two terminal I should take it? Between what terminals it is acting as inductor or capacitor?
So Vin and ground. So Vin will be with respect to ground, right? So if I
Okay.
write, so Vin and this ground. So this ground is for the entire circuit. This has plus VCC minus VCC with respect to this ground, and this is also ground. So if I consider this entire thing in a box, with common ground. So between V in and that ground, we'll get inductor of this value R square into C for this condition. When we consider all to be R and Z4 to be 1 by C, then this is the condition.
Okay. Can we scroll up? Just I'm curious about the circuit. Here V in and V out are shorted, right? Virtually.
V in and V out are shorted. Yes, basically our V naught is same as V in, but this is not our output. Need not be our output voltage, because this I have represented as V naught connected to another resistor, but this may or may not be our output, because the entire objective is I have to connect a circuit so that when I look it from the input point, then it will look like an inductor. So this entire circuit has two terminals. One is VIN and ground. Between this VIN and ground, it will work like act like an inductor.
Okay. Other side also, right? Between
Uh-huh.
load also, it can act as a inductor
Yes,
capacitor, right?
yes, it is
Okay.
symmetric. Only this ZL, if you bring it over here, then
Yes, yeah, correct.
because it is just symmetric and until this point, if you exclude ZL. So you can play with ZL, you can keep it that side and it should work same because it is symmetric.
Okay. And it is a pure capacitor. It doesn't having any ESR related things here.
Capacitor will have ESR, but we have neglected that ESR because
No, no, no. I'm not talking about that. I am talking about the output capacitance, how it is getting. Right? I
which
mean, the capacitance, right? When we keep Z4 is equal to inductor, then we'll be having one capacitance value,
yes,
right?
yes, 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 yes.
So that capacitance is doesn't having any IESR value.
Only if the inductor does not have any DCR. So inductor has yeah, this is also one good question. Ideal inductor will be like this. So this is ideal, and non-ideal will have some parasitic resistance in series, and this is named as DCR, DC resistance, and this is non-ideal. So if you consider non-ideal inductor, then you will get R plus JX. So as if R is ESR of the capacitor. Got it?
Yeah, got it. Thank you.
Okay. Yeah. Okay. Now we'll quickly go to our problem solving session. We'll quickly solve few problems, and these are very simple. Only you need to know the uh, basic concept, which I think you have already understood. So let us solve few problems.
So these problems are all are ideal based only, right? No
Yes,
practical.
yes, yes. All are ideal based, but if they say non-ideal, then you have to solve it in the way that I have explained earlier in this session.
Oh, okay.
Okay, so first we'll start with this problem. So for today, I think it will be problem 3, because we have discussed already 2 problems. So this will be problem 3 for today. So first of all, the circuit may look complicated, but it isn't. So it is assumed to be ideal op amp. So now we know that for ideal op amp, this current is 0, and this terminal is also short circuited with this. So this is also 0. I mean grounded. So current here is not there. So whatever current is coming over here is going over here, and this is ground because they are internally shorted. Now you apply KCL. Apply KCL. Can you tell me the equation? What will be the equation?
0 minus V1 by R1.
Okay, but I have considered that direction to be in this.
Okay, V1 minus 0 by R1. V1 by R1.
So V1 by R1 is 4 by R1 is 4K is equal to
Outgoing current. 0 plus V2
Okay.
minus
So,
V naught.
okay, V2 minus V naught, 2 minus
V
V naught,
naught by
R2, right? 4K. So now this side
yes.
will cancel 1. I will get V naught to be minus 2, right?
Yes, minus 2.
Minus 2. So it is like inverting, but the voltage is minus 2. Input is how much? 4. Okay. So we'll check. And also there is less than a minute. And if this meeting can kindly join, then we'll continue our session. So V naught is minus 2. Okay. Now we'll solve this circuit. And one more thing. Okay, let this meeting end, then I'll make another announcement when we join back. So problem 4. So in this circuit also they have connected in this way and they're asking V naught. So first of all, these are internally shorted. So this is our ground. So this is our last week, but there will be another session. So till now we have taken 12 sessions, problem solving sessions, and there will be another session, final session before your final test for this course, which will be the last session, and it will be a 1 hour session. So in that 1 hour session, you can ask doubts, but I am planning to just revise whatever we have discussed. So I'll just open my notes from week 1 and I'll just scroll down and I'll just summarize what we have learned in this like entire course. So I'll just summarize my 12 notes, but if you have any doubts, you can ask me. So it will be just some interactive session, and if you have any like queries in particular concepts, so whenever I go to that link, you can ask, and it is just like a summary, 1 hour summary, and yeah. So there will be another session on Wednesday, similar to my session. The other TA who is taking tomorrow, he will also be having another 1 hour session. And mine is Wednesday, probably 6 to 7, maybe 7 to 8. I don't know which one I have selected. Most probably it will be by Wednesday, day after tomorrow, 6 to 7. And I think he has selected on Thursday. So you will get another notification in the same meeting link, a Zoom meeting link, and that will be our last session. Yeah, so if you still have any doubts in the previous week and if you still confused about it, then we can discuss in that session. So first of all, this is ground. So this is also ground. And this is ideal. So the current is 0. So now I can say, so first of all, they're asking what is V naught. So how will I solve? First, I'll consider the current direction. Say the current direction is like this, then that current will enter over here, and then that current will go over here, right?
Right.
Yes. So first say this is I1, this is I2, then this one will be I1 plus I2. So this is ground and V1, V2, R1, R2 are given. So I can calculate I1, I2. So can you tell me what is I1?
V1 by R1,
V1 by
I1,
R1. So it will be 1 by 4, which is 0.25
25,
times
1 by 3,
1 by 3. So it will be 0.3
0.33.
milliampere. So now what is my V naught?
V naught is equal to
0 minus
V naught is equal to
from here, this current. 0 minus this current into resistor is V naught, right?
yeah minus I1 plus I2 into R3.
So 0.25 plus 0.33 into R3 is 2K.
2K. Yeah.
So if you calculate,
1.16.
how much are you getting?
1.16.
Okay. Minus 1.16 volt. So this is our V naught. Okay, so let us go and check. So it is minus 1.16. So it is within this range. So others are, were you able to follow how we have solved? So first of all, this is virtually shorted. So if this is ground, this is ground. And also no current enters the op-amp because it is ideal op-amp. So all the current that is coming from over here will pass on or enter through I3. So V1, V2 are given. First, we have calculated I1, I2 because I1 is V1 minus 0 by R1 and I2 is V2 minus 0 by R2. Then after getting I1, I2, V0 is nothing but 0 because this terminal is 0 minus I1 plus I2 into R3. So using this equation, we got V0 minus 1.16. So is this clear?
Yes, sir.
Okay. So now we'll go to the other problem, problem 3. So they have given V supply minus V supply, but while I write, I might or might not write because it is assumed that the op-amp has supply. Sometimes I don't write. It is again up to your convenience. You can write, you may not write also. So this is our problem 5. So here also they are asking V naught. So this is problem 5. So for any op-amp, first you have to, what you have to do is they are virtually short and current is 0. So this is V1 is how much? 3 volt, right? So this is 3 volt. So this is how much?
3 volt.
3 volt. And V2 is 1 volt. So this is how much?
1 volt.
V2 is 1 volt. So this is
V2 is 2 volt. 2
2
volt.
volt. So this is 2 volt. And current here is 0. And current also here is 0. So I can write, so this is like a resistor divider circuit, right? So R2 by R1 plus R2 into V0 equal to 2 volt, right?
2.
And R2 is how much? 10. R1 plus R2 is how much? 15 into V0 is equals to 2. So V0 is 30 by 10. How much is V0? 3 volt, right? Agree? Hello?
Yes, sir.
Okay.
Yes, sir.
Yeah. So like everything is based on two things. The input current of an op-amp is 0 and the inverting and non-inverting terminal are virtually shorted. So for any problem, so even if say this seems complicated, but we just have to rely on those two aspects and we can solve any problem. So now this is our problem 6. Not this. So this is our problem 6. So for any given problem, first I'll consider that two aspects, then I'll start solving. So here also I'll consider the same thing. Okay. So first of all, this voltage is same as this voltage and the current here is 0 and current here is also 0. Got it? Now V1 is given 1 volt. Sorry. V1 is given 1 volt. So this is 1 volt and V2 is given 5 volt. So this is 5 volt. Okay. And this terminal say voltage is some V dash. So apply KCL. Current entering here will be equal to here, right? Agree?
Yes.
So if we apply KCL, we will get what? 1 minus V dash by R1, which is 4K, is equals to V dash minus 5 by
Out.
R2. R2 is how much? 3K. So now if you do, it will be 3 by 4 minus 3 by 4 V dash is equals to V dash minus 5. So it will be 23 by 4 is equal to 4 plus 3, 7 V dash by 4. So we'll get one equation, which is V dash is equals to 23 by 7, right? Hello. Do you agree? B dash is 23/7. Hello. Others, can you
Yes,
just check? Yeah,
yes,
okay.
sir.
Okay. So now I also know that current through R3, so this current will be same as this current, right? Because current entering op amp is 0. Agree? And this is
Yes,
at
sir.
5 volt and this terminal is at V dash. So now I can calculate IR3. IR3 is 5 minus V dash by R3. R3 is how much? 3K. So if I do, it will be 5 minus 23/7 by 3K. So 5 minus 23/7 is how much? 35 minus 23. So 12 by 7 into 3K. So from there I'll get IR3 is equal to 4 by 7 milliamperes. Right?
Yes.
Now what will be the V naught?
V dash minus V naught by R4.
V dash minus IR3 into R4, right?
Yes, yes.
So V naught is V dash minus IR3 into
Yeah.
R4. So V dash is 23/7 minus IR3 is 4/7 into R4 is 2K. So 8/7. So this will be 15/7. So it will be how much? V naught is
2.142.
2.14. 14 volt. So let us go back and check. V naught is 2.14. So V naught is 2.14 within the range. Okay. So now what we have done is again the same thing. Input current is 0. So this current is 0. Then these two are virtually shorted, but I do not know this voltage. So here I have applied KCL because I know this terminal, this terminal, this resistor, this resistor. So first I have calculated V dash. Once I get V dash, I know this voltage and I know this voltage. Also, I know the current through R3 is same as current through R4. So first I have calculated current through R3. So which is the same current that is flowing through R4. So if you apply KVL between these two terminals, I'll get V dash minus IR3 into R4 equal to V naught. So from there, I'll get V naught. So every problem is simple. Only I'm using two things. One is the current entering is 0 and both the terminals are virtually shorted. So now let us solve the other problem. So this week is very simple, provided you have understood the concept. This is problem 7. Okay, so this is problem 7. So first of all, these two are virtually shorted. V2 is how much? 4 volt, right? This is 4 volt. This is 4 volt. This is also 4 volt, right? And current
Yes.
entering here is 0. Current entering here is 0. So all the current that is flowing here will go over here, right? Agreed?
Yes.
And what is IR1?
IR1 is 0.
Okay, IR1 is, or we'll directly apply KCL there. Then we'll get 4 minus 4 by R1 is equal to 4 minus V naught by R2, right?
Yes.
So what is V naught?
4.
4, yes. So V naught equal to 4 volt. So this is also very simple. They have given, so no current is basically flowing. So as no current is flowing, the potential will remain same in that branch. So V naught is equal to 4. So V naught equal to 4 in this range. And yeah, this also we can solve. This is another type of question. Everyone is following, right? You are able to understand, all of you?
Yes, sir.
Okay. So now we are at problem 8. Okay, so this is what voltage V1? How much?
4 volt.
4 volt. And first of all, this current is 0, and this current is also 0. So what is the voltage here? This terminal?
4 volt.
4
4
volt.
volt.
So this terminal is also 4 volt, right? Agree?
Mm,
Now current entering here will be current going like this, right? Agree? The same current will flow
yes.
through R2. So
Yes,
apply KCL. So can you tell me the equation?
V naught minus 4 by R1 is equal to 0.
V naught minus 4 by R1 is how much? 2K
Is it
is equal
okay?
to
Is 4
4
minus
minus
0, 4
minus
minus V2, that is 6.
minus 2. Oh, so 4 minus 6 is minus 2, or maybe I'll write. Then it will be easy if you check. So 4 minus 6,
Minus 0 divided by R2. R2 is 4K.
4K. So this goes here 2, then it will be minus 1, right?
Minus 1.
So that equals
3 volt.
3 volt. So V not equal to 3 volt. So let us go and check. So V not equal to 3 volt. Yes, it is matching. Is this the same? It is somewhat a different question, and this is very simple. But all are in the same format. So we have problem 9. If you see, we have solved so many problems with in very less time because they are very straightforward and very simple. Whereas in other weeks, they are also simple, only they are lengthy. So how much is V1? How much is V1?
4 volts, sir.
4 volt. So what is voltage?
4 volt.
So what is this voltage?
8 volt.
8 volt. So it is just straightforward, and there is nothing in this question. So V naught is 8 volt. So we'll go and check. So V naught is 8 volt. Okay. And yeah, this question also they are asking V naught. But it is also in the similar format. So this is our problem 9. This is our problem 9. Okay. So how much is V1?
4 volt.
4 volt. And then what is this voltage?
4 volt.
4 volt. Okay. And this current is 0. This current is also 0. So this is like a resistor divider, right? So
Yes. V naught into
V naught into R2
R2 by R1 plus.
R2 by R1 plus R2 is equal to 4 volt, right?
Yes.
So how much is V naught?
8.
V2. So what about others? Are you able to follow? Others? Do you have any doubts until this point?
Looks like we are quick.
Yeah, we are, because these are very just simple problems. Only looking at them we can solve. But no one has joined in the last week. Any reason or you are busy? Okay. No one wants to say. Fine.
I think festival season, right?
Festivals. Oh, okay, okay. That's also true. There are Telugu festival and Muslim festival last week. So this is problem 8, problem 9, then problem 10. So this is 9. Yeah, but it is very good interacting with you all. Yes, sir. Festival. Okay, okay. Got it. I forgot.
And maybe we can discuss about that R3 and V2 at V0 terminal, right? The
R3.
significance of that.
So there is no significance because V0 is not determined by R3 and V2, but the current through R3 is determined by V0. So V0 is independent of R3 and V2, but current through R3 is dependent on V0. So V0 is coming 8 volt. Now if I say what is IR3, so IR3 is 8 minus
8 by
V2
2 4
by
by
R3. R3 they have not given because it is not required. So V4 they have given, V2 they have given 4, so 4 by R3. So that's why they have given. So even if I consider multiple resistor and sources similar to this way, V0 will still be 8 volt, but the current through that is determined by V0 and those resistors.
but this is a minimal load condition, right?
Yes,
Uh,
because it is ideal op amp, it is happening like that, but in the other case, it will have some dependency. All these are ideal op amp. Even if they are not ideal, the input impedance is very, very high and gain is also very, very high. So the answer will not be exactly 8, but close to 8. If they become very, very high, then you can consider to be ideal and you can proceed in this way. So this is problem 11. So V2
I
then.
mean, just I have question related to
Okay,
that
okay,
previous
okay,
problem. Right?
okay, okay. Sorry, no, continue.
So here, for example, the output maximum output current driven by the op amp is 8 milliamperes. Let us say.
Yes, yes.
Okay. So R3, let us say it is 5 kilo ohm.
Okay.
In that case, uh, the circuit is feasible
Yes,
still.
yes, yeah. It's a very good question. So one of the issue in like our lab that we also face is the amount of current that it can supply. Say, I'll give you one quick example of what we do. So there is, okay, let me draw. Then it will be good that you have pointed out. So we have this series RLC circuit. So here we have function generator, and function generator output is connected to resistor and then inductor and then capacitor, and it is connected to its ground. So in the function, function generator, right? So in the function generator, we give say 1 volt uh, square wave. So 1 volt square wave we are giving. So it is toggling between 0 and 1. 0 volt, 1 volt, 0 volt, 1 volt. Now say the resistor I have selected 100 ohms, and this is LC, and say I'm operating at resonant frequency, something like that, and the current is, say, neglecting L and C, the current is coming I, nearly how much it will come? 10 milliampere, right? Right?
Yes, 1 by 100.
But say the requirement of this is 20 milliampere only. Now I will change my resistor to be 10 ohms. So now the current will become 100 milliampere, right? Right?
Yes.
But it can only supply 20 milliampere. So in this case, what happens is it will not be able to provide. So here itself, it will not provide like this. So the like shape is somewhat different. So instead of square wave, it is coming like it should be like this, right? But it was not like this. We have actually faced this issue. So it was some different shape and square, and here also some different shape and square. So it is not coming square. So this is called loading effect because the function generator is not able to supply the current that the load is drawing, it will get distorted. So it will not be able to maintain the same voltage that we asked. So because the current is 100 milliampere, so now the voltage will be changed accordingly so that the current will remain 20 milliampere. So it will not be able to provide that current.
Maybe the voltage is, for example, 1 volt multiplied by 20, so that is 20 milliwatt power, right?
Yes, 20
It can then.
yes,
So
yes,
when we use 100 milliamperes, the V into I is equal to 20 milliwatt.
yes, yes,
So our voltage would be divided by 100. Right?
yes, yes, yes. Are you able to see my screen?
Yes, I think it is loading.
Yes, yes, loading. This is the first part of the series RLC experiment, which is transient. Were you able to listen to the audio of this
Ye- Yes,
video? This video audio, can you listen? What I was saying this.
yes, yes,
Okay, okay, then fine.
yes.
This is the first part of the series RLC experiment, which is transient response. We are giving a square function of 50 hertz, which is very less frequency, and it is connected to the resistance decade box, and the resistance value is 200, and the inductor value is 0.1, which is connected to capacitor in series, and the capacitor value is 0.1 microfarad. So in this point, if you see the input, I have given step, but it is not exactly step. It is kind of oscillating, right? Because the output voltage is oscillating, the current is also changing, and that's why it is not exactly step. You see, the V naught is not exactly step. It is getting loaded, and that's why it is not exactly step. Output. Also, this is underdamped case where the resistance is very less, so current is more. So that's why the current is more because the resistance is small. Response of the RLC circuit. Green waveform is the capacitor voltage, and the yellow waveform is the input step voltage. So now the resistor is 200 ohm, and we can increase the eta by increasing the resistance. So now I'm increasing the resistance to 500. So as you can see, the eta has been increased. Now I'm increasing the resistance to 900. Now I'm increasing the resistance to 1.9 kilo. And now I'm increasing it much higher. So now if you see, it is perfect step, right? There is no that
Hmm.
oscillations because the resistance is very, very high. It is able to supply that much current. But previously, if you consider here, if you see, it is not exactly step because it is loaded. Whereas in this case, it is slightly loaded. If we move further, it is not at all loaded and it is having that step function. So that loading effect will come and that will distort this waveform. So that will happen here
Just
also.
50 hertz, right?
Yes,
That was.
that is any frequency, but the current is actually causing that issue. Got it?
I mean, maybe for the higher frequencies, your
Higher frequency.
probing probes.
Sorry, continue.
Yeah, maybe a higher frequencies case, probes may come into the picture, so we can see those behavior, that type of behavior, right? Due
Uh,
to transmission.
Actually, that behavior is solely dependent on the current because for the same frequency, if I reduce the current drawn by the circuit, it is getting reduced. Like the effect is.
Indirect
uh,
or indirectly we are absorbing those reflections by using the resistor values. So
y-
if we go higher resistance, power will be reduced.
Yes, yes. Actually, the objective of that circuit is to check overdamped, underdamped, critically damped case. So I have made a video on that. So for the overdamped case, we need to provide higher resistance. So as a part of the experiment, I have performed that experiment. And while looking back at the video, me and my professor have observed that it is getting loaded, but as the resistance is increased, it is not loaded because the current drawn is less. So that's why it is like proper step. Else it is not proper step. It is bit oscillating. So the input step itself is not proper because the function generator has minimum current requirement. Whereas if you take some other equipment, which has enough driving capability, which provide enough output current, then the step function will be proper, and it will be giving proper step. Yeah, but this with the equipment that we have in our lab, this is creating that issue. Yeah. Is that clear?
Yes, yes.
Yes, sir.
If others have any doubts, they can ask. So, okay, fine. So this will be our last problem for today. So V1 is how much? 2 volt, right? So this is 2 volt, and V2 is how much? 1 volt. Okay. And the current here is 0. The current here is also 0. So now what will be this voltage?
V1 by 3.
Okay. So V dash is R2 by R1 plus R2 into 2. So R2 is not V1 by 3, right? It is 2 by 5 into 2, right? So 0.8,
1 second. Yeah, R2 is 2. Okay, 2 by 5. Yeah.
0.8 volts. So this is zero point 0.8. So if this is 0.8, this is also 0.8,
Right.
and the current flowing through this will also flow through this. So I'll calculate IR3. IR3 is V2 minus 0.8, 1 minus 0.8 by R3, 1K. So it is 0.2 milliampere.
Right.
Now if I calculate V naught, it will be how much? What is the expression?
0.8 minus V0 by R4.
0.8 minus IR3 into R4.
V0. Yeah.
0.2 milli into R4 is 2K. So how much is my V naught?
0.4
0.4 volt.
milli.
0.4 volt, not milli.
Volt. Oh, yeah, correct. Milli into 2K. Cancel out.
It's cancelled out. So this is our V naught. So if we go back and check, it is 0.4. So it is matching. Okay, so with that, I will conclude this session. So let me just quickly summarize what we have discussed. So today we started with the op-amp basics. We have seen the IC741 pin configuration and the op-amp schematic representation, and then we have seen different regions in the working of op-amp. So this is the amplifier. So in this region, it is getting saturated. But for ideal op-amp, if we consider, it is acting like a comparator, because if the voltage is more than this, then it will be plus VCC, else it will be minus VCC. And we have seen the non-ideal op-amp circuit connection and how it is working like an amplifier, and we have seen what are the input impedance gain as well as output impedance for ideal op-amp. And then we have discussed about inverting amplifier, and then we have discussed one key aspect, that non-inverting and the inverting terminals act like virtually shorted. And then we have seen if an inverting amplifier is connected with resistors for ideal op-amp, what is the V naught, and in the case of non-ideal op-amp, what will be the case, and it will come close to -2 but not exactly -2. Then we have also seen non-inverting amplifier where output is positive, and output is always greater than or equal to V8 because we have this one plus term, followed by differential amplifier. So it will just amplify the difference between the two terminals. So it will be the difference between the non-inverting terminal and inverting terminal. So this is positive, V2 minus V1, and output is also the scaling factor of this one. Then we have quickly discussed about integrator and differentiator using this inverting amplifier configuration. Then we have discussed about this general impedance transfer circuit where you can emulate inductor using capacitor. Then we have solved few problems, and all the problems we have considered only two aspects. One, for ideal op-amp, the input current is 0, as well as these two are virtually shorted. So whatever the voltage is at non-inverting amplifier, it will be reflected at the inverting amplifier, and also the current entering these two non-inverting and inverting terminals is 0. So first you see write the whatever currents are 0, and then followed by voltages, then you will be able to apply KCL, and you will know where exactly you need to apply KCL, and you'll be able to solve any complicated circuit. So yes, with that we can conclude this session, and we'll have another 1 hour session on Wednesday, probably at 6 p.m. You will get a Gmail email reminder from the NPTEL people. If you have any
Would you spare 2 minutes?
yes, yes, yeah.
Uh, so there are two questions, right?
Okay.
For example, if I want to understand whether it is op amp is working in amplifier mode or
Mhm.
it is acting like a comparator,
Comparator.
how do we come to know? Yeah. So
Okay.
in order to push from amplifier mode to comparator, how
Mm.
can we push it? This is
Okay.
one question.
Okay.
And the second question related to oscillators, right? By using the op amps, when it will be acting as a oscillator. Yeah.
Okay. So we okay. The first question, first of all, how when it will work like an amplifier and when it will not work like a or when it will work like a comparator. So we have already discussed over here. So if the op amp is having just two inputs, I have considered one example here. So if the op amp is having say only two inputs, where here if you have only two inputs and no negative feedback, then it will and if it is an ideal op amp, so then what happens, this is the v naught and v2 minus v1 graph, right? So if v2 minus v1 is positive, then it will be plus vcc. If v2 is less than v1, then it will be minus vcc. So in this case it will work like a comparator. But if there is any negative feedback, which means there is a connection between this inverting terminal and this V naught, then it will not act like a comparator. Instead, it will work like an amplifier. So in any problem where you see this connection between the negative and V naught, there may or may not be resistance, then still it will be a negative feedback. In this case, it will work like an amplifier. So mathematically also you can do. So in this case, sorry. So in this case here, we have considered the op-amp graph and then we got to know it is acting like a comparator. But in this case also we have considered the ideal cases, but we have got V naught, which is a scaled version of V1. So whenever there is this negative feedback, then it will act like a inverting amplifier. So does that clear your first query?
I mean, uh, some situations where the hysteresis is right, at
Yes.
that time we'll be considering that as comparator. So even though we have a feedback.
So there are again two different so this is just the theoretical application. Okay. So now
Okay.
uh, so in practical application, there are two different ICs for op-amp as well as comparator. So in the case of comparator, it is a three terminal device. So input, output, and so input, two inputs and one output. So the IC itself is made like a comparator. You cannot make it work like an amplifier. In some other ICs, it they directly say it is an op amp. So it works like an amplifier, and you have to use in any one of these condition. Like say, in my case, I use this differential amplifier. So that op amp itself will work like an amplifier. So in the practical situation, if you want it to work like a comparator, then there are comparator ICs, and then if you want it to work like an amplifier, then you have to buy an op amp and then connect the circuit. But instead of now here there is a negative feedback. If you remove this and connect only two things, then it will still work like a comparator.
Okay.
And for the op amp to be made into comparator, the gain should be very high. So if the gain is very high, then it is close to comparator because there is no linear region or very small linear region. Again, there is less than a minute. So if this meeting can kindly join, so we can continue our discussion. And if we want to work like an amplifier, then there are some methods to make this linear region more. The gain will be smaller, but there will be more linear region. So we can apply more input voltage and still the output is like an amplified version of the input. So there are few methods like compensation of op amp they say. So, but we'll not go into that, but there are methods and they'll make. So if you want to make it work like an amplifier, operate in the linear region. If you want to make it work in a like a comparator, keep it in the saturation.
Okay.
Okay. And another thing that you said about oscillators. So coming to the oscillator that you have said, so for oscillator they'll not use op-amp, they'll use something called inverters, the CMOS inverter. So they'll connect back-to-back inverters. So inverter is drawn something like.
I am saying positive feedback op amp amplifier.
Okay, okay. Then okay. That oscillator. Then they'll connect in positive feedback and like the make the circuit in a way that it will be toggled between plus VCC minus VCC. So I have to check the circuit. I don't remember the oscillator circuit of op-amp, but it will also be connected in a positive feedback. And because of that, the output will get become more and more, and it will get saturated at V naught, and again because of the circuit, it will come back. So it will be oscillating between plus VCC minus VCC, and it will keep on oscillating. So once it gets started, it will keep on oscillating. But there has to be some trigger point, then it will get started. Same with the digital oscillators also. So it is just back-to-back inverters. So I'll just complete. So it is just back-to-back inverters, 1 0 1 0. So okay. So it will be back-to-back inverters. I think it should be even number. So it will be just the back-to-back inverter connection. So it is say 1 0 1 0 1. It will get keep on shifting because no, I think then it should be the other way. Then only it will change. Sorry. So if it is odd, then it will keep on changing. It will keep on toggling. So in this case, what happens is they'll start with 1, and here there will be time delay, right? Here, in order to come here, it will have TD delay. Here also it will have tau d delay. Here also it will have tau d delay. So now if we trigger it with 1, so 1 will be inverted to 0, and 0 will be inverted to 1, and 1 will be inverted to 0. But the moment we have given 1 and the moment it has come to 0, there is some delay. So now this 0 will again come here. So now 0 will come here, and then it will get delayed and come 1 0 1, and again it will go back here 1 0 1 0. So it will keep on oscillating between 1 and 0, and here the time period is defined by the propagation delay of that. So this is the digital version of oscillator. Whatever you have said, that is the analog version of oscillator, where they use op-amp circuit positive feedback, and they use. But that circuit you need to check. I don't remember the exact circuit of the op-amp based oscillator.
Why I have this question is in some networks problems, right, where we will be having both side. P side also we have feedback, and N side, I mean negative side also we are having feedback.
Yes. Yes.
So two feedbacks are present.
Yes.
So there I could not understand that which mode it is operating, whether it is in operating in amplifier mode or it is in oscillator mode, how to figure it out. That was the problem.
Okay. Got it, got it. But if you have read the oscillators, and if that circuit is falling in that oscillator domain, then you will know that it is working as an oscillator. But as far as this course is considered or many such relevant, we will not go into positive feedback. Uh, the entire course is based on the negative feedback, so we will not have that question of whether it is working as an oscillator or comparator. So that problem is not there. So for this course, the syllabus is only the negative feedback, where uh, these two things are met. Like both are virtually shorted, and the current entering is 0. Whereas in the case of positive feedback, you cannot consider that. So that problem will not arise in this course. Yeah, but that is
Yeah.
how to understand oscillators, how to work on the positive feedback circuits. Yeah, that also that is there. That is a separate topic, but that is not there in this course.
Okay, thank you.
Okay. Yeah, if others have any questions, you may ask, else we can end this session today.
Sir, in the last question,
Okay.
sir, last, sir, please show the.
Sorry, can you speak louder? Your voice is not audible.
Sir, in the last question,
Uh-huh.
sir, first, sir, please show the question.
This one.
Yes, sir. Yes, sir. Sir, how we are getting 0.8 volt Both the ends, sir.
Okay, here and here.
Yes, sir.
Okay, because this is an ideal op amp and this is a negative feedback. We have seen that these two terminals are virtually shorted. So this plus terminal and minus terminal are virtually shorted. And this plus terminal I got pointed because the current here is 0. So basically 2 volt is being divided among R1 and R2. So this V dash is R2 by R1 plus R2 into 2 volt. For the given R1 and R2, I got V dash pointed. So if this positive terminal or non-inverting terminal is at pointed, negative terminal or the non-inverting terminal should also be at pointed. So if this is pointed, this should be at pointed. So now because this is pointed, I have calculated IR3. And we know that current entering op amp is 0. So IR3 is equals to IR4. So I got IR4. Now 0.8 minus IR4 into R4 is V0. So using that expression, I got V0.
Yes, sir. Okay, sir. Thank you.
Yeah, it's a nice session interacting with all of you. Many good questions that you have asked, and I hope I was able to explain and you were able to understand all the concepts.
Okay, it's just last question, right? If you go to the same problem, last problem. Here, right, R3 value, if I try to keep that as 1 ohm or 2 ohms, let us say.
Yes,
So in that case, we'll be having a higher current which is flowing through that, right?
yes,
1
yes,
minus point eight
yes,
five one.
yes,
So the gain will be like zero point 0.8 minus some higher value. It will turn out as negative
yes,
voltage, right?
yes, yes.
So if I try to push this number to supply voltage, let us say dynamically.
Mm-hmm.
So at any one point, if I try to push this V0 voltage to any positive supply or V supply,
Uh-huh.
then this still will be acting as an amplifier, or else it will be acting as a comparator at that time.
Okay.
From there onwards, from
Yes,
there.
yes, yes. There are again two things. One thing is in the datasheet, every time they say you operate as an amplifier, they'll provide some resistance value that it should be within a few kilo ohm range, else the op amp will get loaded and it will not work like an amplifier, not exactly like an ideal op amp. So there are
Okay.
while choosing these resistance, that's why people always select in terms of 1k, at least 1k, 10k, 30k, 40k, else it will not act like an op amp and you will not get the expected V naught, because now we cannot apply whatever these two things that we are applying for ideal op amp. So when you keep very less resistance and then you apply these things, things may not work exactly the same way as you have applied when the R3 is very high. So that the two conventions or the two assumptions that we have considered may or may not be valid. So we cannot directly say that V not will be this zero point 0.8 minus R3 into I3, because this current may not be 0. Then this might be drawing some current. So we cannot say that.
Yes. I mean, minimum current, like in the
Uh-huh.
sense of microamperes, it is drawing, let us say.
Hmm.
So it is not going to have much impact on the eye, right?
Hmm.
So generally, it will be having mega ohms of impedance. So it is drawing microampere
Microampere.
current, let
Uh-huh.
us say. So
Yes,
in
that V
that
naught can be
direction,
negative, huh?
yeah, so what I'm thinking is for dynamically V2 is changing, let us say,
Mm-hmm.
since the output voltage is depending on V2 minus zero point 0.8, right?
Mm-hmm.
So the current, right? So the current
Yes,
value.
yes,
And there also on the top side also, if I try to push this V1 to nearly to the supply voltage,
yes,
then it will be acting as a comparator, right? Since it is already saturated.
yes, yes,
Saturated.
yes.
So from there onwards, like, is it possible to have oscillator behavior and comparator behavior for
No,
a same op
actually,
amp
see,
at different?
no, no, like there are two different things. Comparator is like for a given input, it will either give either plus or minus. So if you fix the input,
Hmm.
it will output is fixed. But in the case of oscillator, it is a iterative process. If you see even in this digital oscillator, if I initially give it one here, and if I leave, this one will propagate till here 0 1 0, and it will keep on changing. So the circuit will keep on working and it will keep on toggling. So if it want to be work like an oscillator, we not should keep on toggling between plus and minus. So comparator is a different thing and oscillator is a different thing. Oscillator, it will keep on as long as you give supply to this op amp, it will keep on toggling between positive and negative, and it will keep on happening. Whereas for comparator, so it is not happening because our inputs are fixed and the output will change according to input. So if you consider this here, this problem, the output will change according to our input. Here, because our input is sine, the output is toggling like this. But this is not an oscillator, because the moment it is triggered, and even you have not given input, it should keep on changing like an oscillator. This is not oscillator. This is acting like a comparator. Oscillator is you should trigger the circuit and it will keep on working for eternity.
Okay. I mean, if the V output is saturated, whether it
Uh-huh.
is on the positive side and negative side, then there is nothing to amplify the signal. So
No.
at that time, we have taken, okay, since the output is saturated, right? So
Yes.
output is saturated, that potential difference between the positive terminal and negative terminal is zero, right?
Mm,
I mean, when we give feedback to that, V naught
yes.
is given feedback.
Yes. When
To
feedback is
the,
given.
when feedback is given.
Mhm.
So now the output of the op-amp is already saturated to supply voltage
Yes.
VCC.
Yes.
Okay. Now there is nothing to amplify the signal and input is not changing at that time.
Hmm. No, no. Like, can you repeat your question? I could not follow.
My question is, for example, V not reached to VCC.
Yes.
It is in the negative feedback, let us say, negative
Now, if
feedback mode.
there is a negative feedback, okay.
Yes, yes. So due to some input side, the
Yes.
output is already saturated to VCC.
But again, like we cannot directly assume like that. So let me. You just tell me the
Okay,
circuit. So here we
okay.
have minus plus. So at plus, what do you want
Yes.
me to connect input?
Input, yes, right,
Okay.
input.
And minus.
From that minus, you are taking the feedback to V naught.
Okay.
Let's say R is equal to 0. V out is directly connected to input.
Okay. Okay.
So
Like,
it is a voltage follower, right?
yes, this is
Yeah,
the voltage follower. So V naught is equal to V input.
right. So how are we getting that V in? Just because of the shorting voltage, right?
Yes.
V in
Yes.
is equal to.
Yes.
So now there is no amplification is happening. So
Uh-huh.
what are the input that we are giving that is coming out as V out? Let's
Yes.
say V in is equal to greater than VCC. So I'm applying some AC input at the V input, let us say.
But even if you apply V in more than VCC, output will still be saturated to VCC. It cannot
That
be
is
more
clipped,
than
right?
VCC.
Yeah.
Yes. Yes.
Okay. Okay.
Yeah. Because output cannot go beyond the power, the supply. Because this op amp is actually made using transistors, CMOS, I mean NMOS, PMOS. So the maximum voltage that it can go is the positive supply of the PMOS, which is VCC, and the least it can go is zero if you have connected it to ground. So that will decide the maximum voltage of V naught. So it cannot go beyond VCC on the positive side, and it cannot go lesser than minus VCC on the negative side. And also for Wien, there are stringent requirements. How higher can you go above VCC? I cannot go to VCC. The IC will get damaged. So there are certain like requirements for the op-amp. So if you open the datasheet, they'll say Wien maximum voltage should be VCC plus 1 volt or VCC plus 0.5. If you give VCC plus 10 volt, then IC will get damaged and you cannot use that IC. So yeah, but V naught is saturated to VCC and minus VCC.
But we can get that 10 gain of 10 or gain of 15, 20. That is possible, right?
Yes,
Amplification gain.
yes, yes.
So
Amplification, non-inverting
non-inverting.
amplifier.
Let us
Yes,
say 5 volt is the VCC, 0.5 we are applying, gain is 10.
wait, let me go to non-inverting. Non-inverting.
In this case, gain is set to
Uh,
10, let us say.
okay,
R2 by R1 I have
is
taken
9.
as 9.
Okay,
9. Vin is equal to 0.5.
okay,
VCC is 5 volt.
okay.
Okay. Vin is equal to 1 volt, let us say. So I want to exceed that
Uh-huh,
one.
uh-huh.
So the output is always like V out
Saturated.
only. Uh, yeah, always V out, right? In
Yes,
that scenario.
yes.
Okay.
So
Just
like,
I want to understand that part.
the circuit is like this. So your circuit is like this. So the gain is 10. The slope is like 10. So when your V2 minus V1 is on, okay, let me just, then it will be good. So let me just take it here. So what happens is, so for this non-inverting amplifier, or maybe I'll go down. So for your case where you have said non-inverting amplifier, I'll write so that people who are watching, they'll also know. Non-inverting amplifier, and you have considered gain equal to 10 and VCC equal to 5. So that will put the restriction on your input that this is plus 0.5 volt and this is minus 0.5 volt. So the moment V2 minus V1 is 0.5, output is 5. But the moment V2 minus V1 is more than 0.5, output is still saturated to 5. But whereas if you come less than 0.5, say 0.4, output is 10. So this is the linear region within which the op amp is like acting like an amplifier. Beyond that, it is getting saturated.
Okay.
Yeah. Similarly, on the negative side,
So,
if input is coming lesser than minus 0.5, it will get saturated to minus VCC.
yes, thank you very much.
Okay.
So many questions I have had.
No. Actually, these are good questions because you are thinking in many ways, and it is actually needed because then only you'll understand. And yeah, these op amps are actually very good, and you'll use in many applications. And I still like sometimes we do not know there are many aspects that come into picture, and when we learn we try to learn from ideal point of view, and then when we implement, then we'll face many issues, then we'll come to know the reasons, then you will know more things about, oh, why this is not working, okay, this is the reason. But the reason is more important. We should not know that it will not work, we should also know why it will not work, and we should also know why it will not be exactly gain 10, why it is close to 9.9. So we should know all these things, then only we will know the overall picture of any concept. And whatever questions you have asked, they're very good, and other people will also get benefited. It is not just for you because this will be uploaded in YouTube, so whoever will be going through this video, they'll also get benefited. And yeah, I'll always encourage more questions, and that will bring like very interesting aspects into the discussion. We can also learn many things, as today I have shown you one video that might have also be beneficial. Yeah, and it was great session.
Thank you very much for your patience
Uh,
and ask questions, for
no,
answering questions.
no worries. I
Thank
should
you.
actually thank you for asking good questions. And yeah, see you on Wednesday, our final session, 1 hour session, which will be just revision. I hope you will all attend that session, and all the best for your assignment 15. Do well, it will be very easy, only you have to make sure you are not making any mistakes. Yeah, your class was very informative and helpful. Thank you, Nia Farhan, and yeah, and I also thank all of you for attending all the sessions and asking very good questions. And I really love these interactive sessions because even after attending 2 hours at the end of the day, I don't feel tired because these are very much interesting, and because you people are very much interactive, and I also love this session. So I always look up to these sessions. So yeah, it is very helpful.
Thank you very much.
Okay. Yeah.
Then
Thank you.
in the
Uh,
next session, right, 1 hour session,
mhm,
maybe focusing on network theorems and
mhm.
phasor diagrams, right? So that
Yes.
will be helpful.
Yes, yes,
And
definitely.
differential equations instead of the conventional method, right? Maybe
Uh-huh.
one or two problems how to solve by using Laplace transforms
Yes,
fastly compared
yes.
to conventional.
Okay,
So these will be helping. Definitely, they will be helping.
okay. I'll just try to summarize everything, but whenever there are easy concepts, I'll
Hmm.
try to go fast. But whenever there are critical
Okay.
concepts, I'll try to go slow. But if you want any problem to be solved, you ask me at that time, so
No,
I can solve at that.
no.
Because I
I
might not
mean,
remember. Uh-huh.
we don't have that much time, right? So
Uh,
maybe everyone will have to.
ask.
So if you want to solve each, if you want to solve one by one, it is very difficult. But
Difficult.
where I'm point, where I'm pointing that concept, like which concepts
Yes.
to be probed.
Yes. I'll try to cover all the important concepts, and anyway, I'll be referring to my notes where I have solved problems. So I'll again try to explain how I have solved. So that will try to like revise your concept as well. And we have covered different type of problems with different challenges. So then you'll also be able to understand the concept. But if you have still have any doubt, you can ask me at that moment so that I'll answer your queries.
Yeah.
Okay.
Thank you very
Okay.
much. Thank you very much.
Yeah. Okay, then see you on Wednesday. All the best for your assignment 15, assignment 12, and good night. Have a nice day. Bye.
Have a nice day.
Yeah,
Bye
thank
bye.
you. Bye.